So the concepts of energy that we've been dealing with in this unit so far are really closely connected to the idea of power, because power is actually just a rate of change of energy. Rate of change of energy. So mathematically, that looks like this. Power is a delta E, so that's a change in energy over a delta T. So notice that's not an absolute energy. You wouldn't plug in just like an EG there, like a gravitational energy, or an EK, a kinetic energy, on top. You're always going to be plugging in a change in energy, or in other words, it'll be an E2 minus an E1, your final energy minus your initial energy, over how much time goes by. The symbol for power is pretty straightforward. It's just P. The unit, so if you notice, you've got an energy over a time, right? So that's a joule per second. But we shorten that. If you look at what's written on a light bulb, it'll be written in watts. The power of that light bulb will be in watts. That's just the short form for a joule per second. So both of those are SI units for power, joules per second or a watt. All right, so here's an example. Let's say you have a mountain climber, and we'll just write our given down here. So she has a mass of 55.0 kilograms. And her Y1, she starts out initially at 850 meters above sea level, and her Y2, Y1, she's going to end up at 2,400 meters. And she starts climbing at 9 a.m. and she ends climbing at noon. So the time that's gone by is 3 hours. Now, right away, notice that that's not an SI unit, so I'm going to convert that 3 hours. So 3 hours, there's 60 minutes in an hour, and there's 60 seconds in a minute. So that lets me cancel out the minutes here, cancel out the hours there, and I get units of seconds at the end of the day. So it'll be 3 times 60 times 60, which is 10,800 seconds. So that's the delta T. All right, so now we're trying to solve for our power. So we know the general equation for power is this. Power is delta E over delta T. What's tricky often is figuring out what should I even put in for delta E? What kind of energy is changing? So this is where you just have to ask yourself, well, what energy is changing here? So what E is changing? Like, she has some kinetic energy, right? She's moving up the mountain, but is that changing? Not really. She's probably climbing about the same speed the whole time. So her EK is probably not really changing. What's changing here is clearly the gravitational energy, right? She's going up to a higher height. So the energy that's changing is EG. And the formula for EG is mgy, which means that what I'll plug into my power equation for delta E here, delta E is going to be an EG2 minus an EG1. So her final gravitational energy minus her initial gravitational energy. So what delta E is in this equation will change from situation to situation. You're going to look at your situation and decide, okay, what energy is actually changing? And that's what I plug in for delta E. And in this case, it's gravitational energy that's changing. So let's actually plug that in. So power is my EG2, so that's going to be mgy2 minus mgy1, her initial gravitational energy, and that's all over delta T. And I'm trying to solve for power, so I've actually got this already rearranged. I don't have to do anything fancy here. So you can plug in your numbers. So she's 55 kilograms, G is 9.8, Y2, that's her final height. And same thing here. Y1, she started out at 850 meters above the ground, and the time, make sure it's in seconds. And then you just plug all that into your calculator. And when we toss that into our calculator, I get 55 times 9.8 times the 2400 minus the 850. You can factor out the mg if you want to there. And divide by the 10,800. That gives me 77.4. The units of power are watts or joules per second. It looks like I've got about 3 sig figs here. So that looks good. So my power, this is the average power that she exerts to climb that mountain, is 77.4 watts. All right, let's try another example. So let's say you've got a car and your car is speeding up from 10 meters per second to 30 meters per second. So let's write these things down. So V1 is 10 meters per second. V2 is 30 meters per second. We know the mass of the car. It's a 1,200 kilogram car. We know the power that it takes to make this acceleration happen. It's 32 kilojoules. So right away you want to notice that is not an SI unit. So we need to convert that. A kilojoule is times 10 to the 3. So the easiest way to convert this is just take out the K and replace it with 10 to the 3. And then you'll have SI units there for power. And what we're trying to solve for is time. How long did it take? So I know my general power equation, right? Power is delta E over delta T, and I could easily rearrange that for time, right? I could do that by tossing it in that little triangle thing, right? That's probably the easiest way to rearrange it. We get our delta T on the bottom there is going to be a delta E over the power. But the question is, what is delta E? Like, what is the energy that's changing? So this is what we always have to figure out. What is the delta E? So what energy is actually changing here? If I look at this car, I'm not told this car is going up a hill, so it doesn't seem like there's a gravitational energy that's changing here, but I am told the car is speeding up. So it looks like that delta E is a change in kinetic energy, and kinetic energy is a half mv squared. So it looks like kinetic energy is the thing that's changing here. So that means what I'll plug in for delta E here, delta E is going to be an EK2, so a kinetic energy 2, minus a kinetic energy 1. So let's try plugging that in. So we have delta T is going to be EK2, so that's a half mv2 squared, minus EK1, that's a half mv1 squared, and all of this is over P. So now I can just plug in my numbers. So that'll be a half mass of the car here. The final speed of the car is 30. And then the mass of the car again. And the initial speed of the car was 10. And all of that is divided by the power, which is 32 times 10 to the 3 joules in our SI units there. So 0.5 there, half times the 1200 times your 30 squared minus the 10 squared. If you want to factor out the half times the 1200, that's fine. And then divided by your 32 times 10 to the 3. And I get 15 seconds, and that actually is working out really nicely because it looks like I've got 2 sig figs. So we're good to go. So it should take 15 seconds for that acceleration to happen.